Welcome back to the course on superconductivity. Today we're going to talk about cryogen and cryocooler selection. We'll first see the difference between the cryogens and the cryocoolers. Then see the cryogen-cooled system and then go over the cryocooler's cooled system. The cryogen-cooled system can be divided into two categories. The first one being the dunking system, where the system is just immersed in liquid or solid cryogens. The second one is the circulating cryogen system, where a flow of cryogen goes through a heat exchanger, installed in a cryogenic container. On the other hand, cryocoolers provide a cold heat exchange surfaces to cool the system through conduction. Below is today's most important graph showing the different temperature range of cooling using liquid helium, neon, and nitrogen. When choosing cryogens, this graph is the first thing to look at since it shows at which temperature the system will be cooled. It is the first factor that is taken into account when choosing a cryogen. The boiling points are highlighted in red because, as seen during the previous lecture, the system will be very close to that temperature. You can see on the video here a typical system cooled in a bath of liquid nitrogen. The second factor is the price. While nitrogen is often really affordable, helium and other low-temperature cryogens can be much more expensive. Note that the prices noted here vary a lot depending on the location, the amount bought, or if a contract is made with the supplier. Cryocooler cooled system are cooled using conduction. Here we will see an example of a magnet cooled by a two-stage cryocooler. This is the two-stage cryocoolers, with this part being the first stage closer to the exterior and the second stage, which is the coldest. The magnet winding, in yellow, is in contact with the second stage to be cooled. The magnet is connected to the HTS lead in the second stage, which is connected to a normal metal lead in the first stage. This is to reduce the electrical loss and the thermal conduction coming from the exterior HTS wires being less thermally conductive and having no joule losses. The second stage is protected by a radiation shield to reduce the heating due to the radiation coming from the shell. The system is also in a vacuum to reduce further the losses through convection. When choosing a cryocoolers, there is two main factors. The first one is as before the operating temperature and the other one is the heat load. The heat load is the amount of heat a cryocoolers can extract from the system at the given temperature. Usually, manufacturer give the table on the left-hand side to show the basic properties of the cryocooler. Also, cryocooler can have one or two stages. Usually, two-stage cryocoolers are chosen to reduce the temperature gradient with the exterior, however one-stage cryocoolers are still made for their high heat load. Cryocooler can be divided further according to their cooling mechanism. The first division is made for the operating temperature. Magnets are commonly operated at temperature above 2 Kelvin, but for other applications, for instance superconducting quantum computing, lower temperature are needed. For below 2 Kelvin the main techniques are magnetic refrigeration, that uses the properties of certain material to warm up when exposed to a magnetic field and cool down when demagnetized, Pomeranchuk cooling, that exploits the properties of helium-3 liquid to solid transition under 0.3 Kelvin, and dilution refrigerator, that exploit the heat of mixing of helium-3 and helium-4 isotopes. On the other side, there is the thermodynamic cycles used for cooling above 2 Kelvin. Cycles that use a heat exchanger are called recuperative cycle and are usually useful for large-scale applications. In this category, there is the Joule-Thomson cycle, the Claude cycle, and the Brayton cycle. Cycles that use a regenerator, which is a thermal storage medium, are often favored for small-scale applications. These cycles can be divided further, considering if they use valves or not. The Stirling cycle, using no valves. And if they use an expander or not, the Gifford-McMahon cycle using an expander, and the pulse tube cycle not. For further readings about the cryocooler cycles and mechanism, refer to the three references at the bottom of this slide. When it comes to superconducting magnet at a small laboratory scale, the regenerative cycles are used. Here is a table listing the advantages and drawbacks of each cycle. The main thing to remember is that the Stirling cycle is used most of the time for HTS magnets because of its small size and weight. The Gifford-McMahon is used for its high reliability in MRI, and the pulse tube is used with dilution cooling for superconducting quantum computing. However, being a rather new method compared to the others, it is still not often used. To conclude, by definition, cryogenics are the fluids used to cool a system. A cryocooler is a machine that cools the system through conduction. Choosing the right cryocooler or cooling fluid is critical for the magnets to stay in its superconductive state. Also, choosing a system that has a cooling power too high can be a financial loss.